Right now, you are moving through space at over 500,000 miles per hour. You cannot feel it. You cannot see it. Yet every second, our entire planet hurtles around a black hole 4 million times more massive than our star, the Milky Way. We thought we understood it. We were wrong. James Webb just revealed a galaxy so vast, so violent, and so full of secrets that everything astronomers believed is being rewritten. From flares erupting at the core to invisible matter stretching millions of light years beyond what we can see. If you enjoy this journey, a like and subscribe would mean the world. Now, prepare yourself. We begin. Look up tonight. If the sky is dark enough, you might see a faint band of light stretching from horizon to horizon. That milky glow gave our galaxy its name. Ancient people thought it was spilled milk from the gods. They had no idea what they were actually seeing. Neither did we. Until now, for over a century, astronomers told us our galaxy was about 100,000 light years across. A massive disk of stars, dust, and mystery. That number appeared in every textbook, every documentary, every classroom lecture. It was wrong. Recent measurements have doubled that figure. The Milky Way may stretch closer to 200,000 light years from edge to edge. And if we count the invisible halo of dark matter surrounding it, that number explodes to nearly 2 million light years. This is confirmed by multiple studies using data from the Gaia Space Telescope and supported by James Webb observations. Let that satisfyingly terrifying number settle in your mind. 2 million light years. Light itself, the fastest thing in the universe, would need 2 million years just to cross from one side of our galactic neighborhood to the other. And here is where it gets stranger. You are not sitting still while reading this. Earth spins on its axis at about 1,000 miles per hour near the equator. Our planet orbits our star at roughly 67,000 miles per hour. And our entire solar system rockets around the galactic center at over 500,000 miles per hour. You are a passenger on a cosmic bullet train. You have been your entire life. Every human who ever lived traveled this same path without knowing it. The galaxy completes one full rotation approximately every 230 million years. Astronomers call this a galactic year. The last time our solar system was in this exact position, dinosaurs had not yet evolved. The next time we return here, whatever exists on Earth will be unrecognizable. We used to think the Milky Way was average, a typical spiral galaxy floating in an ordinary corner of the universe. James Webb revealed something different. Compared to similar galaxies, ours has an unusual structure. The inner disk is flatter than expected. The density of stars does not follow the simple patterns astronomers assumed. Our home is weirder than we thought. The telescope's infrared instruments can see through the thick dust clouds that blocked previous observations. For the first time, we can peer into regions that were completely hidden. Stars that were invisible now glow in Webb's detectors. Structures that existed only in theory now appear on screens at research centers around the world, and what those images revealed is forcing scientists to redraw the maps. The Milky Way is not just bigger than we believed. It is more complex, more violent, more ancient, and more alive with activity than any previous generation could have imagined. But size is only the beginning of this story. Because at the center of all this chaos, something waits. Something so massive that it warps space and time around it. Something that just revealed behavior no one predicted. And you are far closer to it than you might want to be. If someone asked where you live, you might say a city, a country, a continent. But your real address is far stranger. You exist on a small, rocky world orbiting an ordinary star, positioned on the inner edge of a spiral arm called the Orion Arm. Some astronomers call it the Orion Spur, because it branches off from a larger structure. Either way, this is your galactic neighborhood. The Orion Arm sits between two much larger arms. The Sagittarius Arm lies closer to the galactic center. The Perseus Arm stretches farther out toward the edge. We float in the space between them, like a house built on the quiet street between two busy highways. From our position, the center of the galaxy lies about 26,000 light-years away. That means the light reaching your eyes from that direction left its source 26,000 years ago. When those photons began their journey, humans were painting animals on cave walls and hunting with stone tools. Here is something most people never consider. We are not near the center. We are not at the edge. We sit roughly 2/3 of the way out from the core. This location might be the reason life exists here at all. Closer to the center, stars crowd together in dangerous density. Radiation levels spike. Supernovas explode more frequently, sterilizing nearby worlds. The gravitational chaos makes stable planetary orbits nearly impossible. Life would struggle to gain a foothold there. At the very edge, different problems arise. Fewer heavy elements exist in the outer regions. Elements like carbon, oxygen, and iron, the building blocks of planets and living things, are forged inside dying stars. The outer galaxy has fewer of those stellar furnaces. Worlds forming there might lack the raw materials needed for complex chemistry. Our position seems almost deliberately chosen, far enough from the chaos to survive, close enough to the action to have the elements we need. Scientists call this the galactic habitable zone. It is a real concept, though its exact boundaries remain a theory still being tested. James Webb is helping refine that map. By studying star-forming regions throughout the galaxy, astronomers can now track where heavy elements concentrate. They can see which zones produce stars capable of hosting rocky planets. They can identify danger zones where radiation would destroy any emerging life. What they found surprised them. The habitable zone might be larger than previously thought, or it might have shifted over billions of years as the galaxy evolved. Our solar system may have migrated from a different location entirely, drifting outward over cosmic time. You might not be where you started. The galaxy beneath your feet is not static. Stars move, arms rotate, entire regions reshape themselves across millions of years. The neighborhood you call home today looked completely different when our planet formed 4.5 billion years ago. But if the outer reaches feel distant and the inner zones feel dangerous, what about the very center? What lurks at the heart of it all? Something hungry, something ancient, and according to James Webb, something far more active than anyone expected. Count to 10. In the time it took you to do that, light traveled nearly 2 million miles. And yet light is not fast enough to visit even a tiny fraction of the stars in our galaxy within a human lifetime. So how many stars actually exist in the Milky Way? The honest answer is, we do not know exactly. Estimates range from 100 billion to 400 billion. That uncertainty exists because counting stars is far harder than it sounds. Think about standing in a crowded stadium at night. You can count the people near you easily, but the crowd becomes a blur toward the far end. Bright lights obscure some faces, shadows hide others. Now imagine that stadium stretches for thousands of miles in every direction, filled with fog and blinding spotlights scattered randomly throughout. That is what astronomers face when they try to count stars. Dust clouds block visible light from distant regions. Bright stars drown out the glow of dimmer neighbors. The galactic center is so densely packed that individual stars merge into a continuous smear of light. And the smallest, faintest stars, the red dwarfs that make up the majority of the stellar population, become invisible beyond a few hundred light years. James Webb changes this calculation. Infrared light passes through dust that visible light cannot penetrate. Webb's instruments detect heat signatures from stars too dim and too distant for previous telescopes. Every observation adds new data points to the census. Here is something that might keep you awake tonight. For every star you can see in the night sky with your naked eyes, roughly 6,000 on a perfect dark night, there are millions more hiding behind them. The faint band of the Milky Way that ancient cultures wondered about contains more individual stars than all the grains of sand on a beach. And each of those stars potentially hosts planets, Current estimates suggest the galaxy contains at least as many planets as stars, possibly more. That means somewhere between 100 billion and 400 billion worlds orbit the stars of the Milky Way. Rocky worlds, gas giants, frozen moons, burning hellscapes, and perhaps, hidden among them, places where something looks up at their own sky and wonders the same questions we do. This is confirmed science now, not speculation. The Kepler mission and ground-based surveys have detected thousands of exoplanets. Statistical analysis extends those findings across the entire galaxy. Planets are not rare, they are everywhere. But here is the twist nobody expected. The number of stars in our galaxy is not fixed. New stars are born every year. Old stars die. The population shifts constantly. Right now, somewhere in the Milky Way, a cloud of gas is collapsing under its own gravity. Within a few 100,000 years, a new star will ignite. And somewhere else, an ancient star is exhaling its final breath, seeding the galaxy with the elements that will become the next generation of worlds. The Milky Way is not a museum. It is a factory, a furnace, a living, breathing engine of creation and destruction. And the most violent part of that engine sits at the center, where something monstrous controls everything around it. Every galaxy has a secret at its core. Ours is called Sagittarius A. Astronomers pronounce it Sagittarius A star, but the name hardly matters. What matters is what it is. A supermassive black hole, 4 million times more massive than our star, crammed into a space smaller than the orbit of Mercury. So dense that not even light can escape once it crosses the boundary called the event horizon. For decades, astronomers suspected something massive lurked at the galactic center. Stars in that region moved too fast. They whipped around an invisible point at speeds that made no sense unless something with enormous gravitational pull anchored them there. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, a glowing ring of superheated gas surrounding a dark shadow. The shadow was not the black hole itself. It was the absence where light could not escape. That image confirmed what physics predicted, but James Webb just revealed something the images could not show: behavior, activity, chaos that never stops. Surrounding the black hole is a disk of gas and dust called an accretion disk. Material spirals inward, accelerating as it approaches the point of no return. Friction heats the gas to millions of degrees, and as that material falls, it does not go quietly. It screams in light. Flares erupt constantly from the disk. Some last only seconds, others blaze for hours. The brightness fluctuates wildly, rising and falling in patterns that seem almost random. Scientists expected some activity. Black holes are messy eaters. Gas does not fall smoothly into the void. Turbulence creates bursts and eruptions. But the scale of what Webb observed shocked the research teams. 5 to 6 major flares every single day, dozens of smaller bursts between them, no period of rest, no quiet moments. The black hole at the center of our galaxy is throwing a constant tantrum, firing off cosmic explosions around the clock. One researcher described it as bubbling with activity. Another said it never reaches a steady state. And here is where the mystery deepens. The flares change brightness at different wavelengths of light, but not simultaneously. Shorter wavelengths dim slightly before longer wavelengths do. The delays range from a few seconds to nearly a minute. This timing reveals something about the physics happening at the edge of oblivion. Magnetic fields twist and reconnect. Particles accelerate to nearly the speed of light. Energy releases in cascades that ripple outward through the disk. The details remain a theory being tested with every new observation. But one thing is certain. The monster at the center of the Milky Way is far more restless than anyone imagined, and the show it puts on is unlike anything else in the galaxy. What exactly causes these flares? What triggers the explosions? The answer might rewrite our understanding of how black holes feed, Imagine a strobe light in absolute darkness, flashing unpredictably, sometimes bright enough to blind you, sometimes barely a flicker, never stopping, never resting. That is what James Webb witnessed when it stared at the center of our galaxy. Sagittarius A is putting on a light show, and it has been doing so for billions of years without an audience capable of watching. Until now, Webb's near-infrared camera observed the black hole for 48 hours total, spread across 8 to 10-hour sessions throughout an entire year. This gave astronomers the longest and most detailed look ever recorded at the supermassive void at the heart of the Milky Way. What they saw was chaos. The accretion disk surrounding the black hole emits infrared radiation as gas heats up during its death spiral. That radiation fluctuates constantly. In the data, researchers watched the brightness rise and fall like a heartbeat with arrhythmia. Then, without warning, massive eruptions, brilliant flares that spiked far above the baseline. One moment the signal showed gentle variation, the next moment an explosion of light, then calm again, then another burst. One scientist compared it to watching fireworks from close range. You never know exactly when the next one will explode or how bright it will be. You only know another is coming. The team counted the activity carefully. 5 to 6 large flares erupted every day. Between them, smaller subflares flickered in rapid succession. There was no pattern they could identify, no rhythm, no predictable cycle. This randomness itself carries information. If the flares followed a pattern, it might suggest organized structures in the accretion disk, hotspots orbiting at regular intervals, clumps of material falling in at predictable rates. The absence of pattern suggests something more turbulent. Material enters the disk from multiple directions. Magnetic fields tangle and snap. Gas collides with gas in violent shocks. The chaos feeds itself, creating conditions where explosions can happen anywhere at any time. Here is what makes this significant for understanding our galaxy. Supermassive black holes are not just gravitational anchors, they shape the galaxies around them. The energy released during feeding episodes can heat gas clouds, preventing new stars from forming. It can also blast material outward, seeding the galaxy with heavy elements. Sagittarius A is relatively quiet compared to the monsters at the centers of some galaxies. Quasars in the distant universe outshine their host galaxies by factors of hundreds. Our black hole is more like a simmering pot than a raging inferno. But simmering is not silent. The constant flares Webb detected reveal that even a calm black hole never truly rests. Energy pours out continuously, influencing the environment around it in ways astronomers are only beginning to understand. And the flares carry another secret. The way their brightness changes at different wavelengths tells a story about what happens in the final moments before matter vanishes forever. A story written in light, at the edge of a shadow that swallows everything. Something strange happens at the edge of a black hole. Light bends, time slows, space itself twists into shapes that defy intuition. And now James Webb has captured evidence of processes so extreme that explaining them pushes physics to its limits. When the telescope observed flares from Sagittarius A, it recorded them at 2 different wavelengths of infrared light simultaneously. This dual view revealed something unexpected. The brightness did not change at the same time in both wavelengths. Shorter wavelengths dimmed slightly before longer wavelengths did. The delays varied, sometimes a few seconds, sometimes nearly 40 seconds. But the pattern held. Short wavelengths led, long wavelengths followed. This timing difference is a fingerprint of the physics at work. Astronomers believe 2 separate mechanisms drive the flares. The large eruptions likely come from magnetic reconnection events. Picture 2 magnetic field lines colliding. When they snap and reconnect, they release tremendous energy. Particles accelerate to nearly light speed. Radiation pours out across the spectrum. This process happens around our own star during solar flares. But around a black hole, the energies are incomparably higher. The magnetic fields are stronger. The particles move faster. The explosions are far more violent. The smaller, rapid bursts between major flares might have a different origin. Gas in the accretion disk does not flow smoothly. Turbulence creates instabilities. Pockets of material compress suddenly, heating up and releasing light before cooling again. These hotspots would rise and fade quickly, producing the flickering behavior Webb detected. Both mechanisms remain theories supported by the data, but not yet proven definitively. Here is why the wavelength timing matters. When high-energy particles spiral around magnetic field lines, they emit radiation. Higher energy particles emit shorter wavelength light. Lower energy particles emit longer wavelengths. As the particles lose energy over time, the emission shifts from short wavelengths to long. The time delay Webb measured matches this expectation. Particles accelerated during a flare emit short wavelength light first. As they cool, their emission shifts longer. The seconds to minutes of delay reveals how quickly the particles lose energy and how far they travel around the magnetic field lines before fading. This is confirmed physics meeting real observations. The data constrains models of what happens near a black hole. It rules out some theories. It supports others. Every flare Webb catches adds another piece to a puzzle that has frustrated physicists for decades. But understanding the physics is not just an academic exercise. These processes shaped our galaxy. The energy released near Sagittarius A over billions of years has influenced star formation, gas dynamics, and the overall structure of the Milky Way. The monster at the center is not just sitting there, it has been sculpting its surroundings since the galaxy was young, and the sculpting continues today in ways we can finally witness. But the black hole is not the only site of cosmic construction. Nearby, one of the most massive clouds in the galaxy is birthing new stars at a furious rate. 300 light-years from the supermassive black hole, something magnificent is happening. Stars are being born. The region is called Sagittarius B2. It is the largest and most active star-forming cloud in the entire Milky Way, a massive concentration of gas and dust so thick that visible light cannot escape. For decades, astronomers knew it existed but could not see inside. James Webb changed that. The telescope's infrared instruments pierced the veil of dust for the first time. What emerged on the screens was a revelation. Hundreds of massive stars, glowing in colors that span the infrared spectrum. Filaments of gas stretching across light years. Dark pillars where even more stars are forming right now, hidden inside cocoons of collapsing material. This is confirmed by multiple research teams analyzing Webb's data. Sagittarius B2 contains enough gas to form tens of millions of stars like our own. The material is compressed by gravitational forces, squeezed by shock waves from nearby supernovas, and stirred by radiation from already formed massive stars. The result is a factory of stellar creation. New stars ignite when pockets of gas become dense enough for nuclear fusion to begin. Hydrogen atoms smash together under immense pressure, fusing into helium and releasing energy. A point of light appears where only darkness existed before, but these are not small stars. The conditions near the galactic center favor the formation of giants, stars with 10, 20, 50 times the mass of our star. These massive beasts burn through their fuel quickly. They live fast and die violently, exploding as supernovas that seed the surrounding gas with heavy elements. Those elements become the raw material for the next generation. Here is something that connects you to that distant nursery. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was forged inside massive stars and scattered across space when those stars died. Some of that material came from regions like Sagittarius B 2 billions of years ago, drifting outward until it collected into the cloud that became our solar system. You are made of recycled stardust from ancient stellar nurseries. The images from Webb show this process in action. Bright red knots mark regions where stars are still gathering mass, still pulling in gas from their surroundings. These protostars have not yet ignited fusion. They are embryos, growing in the dark. Surrounding them, older stars have cleared out the gas nearby. Their radiation and stellar winds have blown bubbles in the cloud. These cavities glow with scattered light, revealing the shapes of the structures hidden within. And threading through it all, filaments of gas stretch like cosmic highways. Material flows along these filaments, funneling toward the densest regions where star formation peaks. The architecture of the cloud is not random. It follows patterns dictated by gravity, magnetism, and turbulence. Sagittarius B2 is a machine for making stars, and Webb just gave us our first clear look inside the engine room. But this nursery is not the only hidden region Webb has exposed. Just a little farther from the center, another surprise waited. 500,000 stars. That is how many appear in a single James Webb image of a region called Sagittarius C. Before Webb, this area was almost unknown. Thick dust obscured it from telescopes operating in visible light. Astronomers knew something was there. The infrared glow hinted at activity, but the details remained hidden. Not anymore. The image released by NASA shows a portion of the dense center of our galaxy in unprecedented detail. Stars packed so tightly, they seem to merge into a continuous glow. Dark silhouettes where dust blocks even infrared light, and strange features that astronomers have never seen before and cannot yet explain. This is where things get mysterious. At the heart of the image lies a cluster of protostars, young stars still forming, still pulling in material from their surroundings. They glow like embers in a fire, their heat revealing their locations even through the surrounding haze. One protostar stands out. It is massive, over 30 times the mass of our star. And it is still growing, still accumulating gas and dust at a rate that will eventually make it one of the most luminous objects in this part of the galaxy. Surrounding this growing giant, the image shows something unexpected. Large-scale emission from ionized hydrogen, glowing gas that has been stripped of its electrons by intense radiation. This emission typically comes from young, massive stars blasting their surroundings with ultraviolet light. But the extent of this emission surprised the research teams. It covers a far larger area than expected. The source of the radiation is not immediately clear. Something is ionizing the gas across a vast region, and astronomers are still working to identify what. Here is another puzzle. Needle-like structures appear in the ionized hydrogen. Thin, elongated features pointing in seemingly random directions. They do not align with any obvious pattern. They do not follow the magnetic field lines astronomers expected to see. These structures might be shaped by outflows from forming stars. They might result from instabilities in the gas. They might be something entirely new. The team flagged them for further investigation. Every answer raises new questions. Sagittarius C sits only about 300 light-years from the supermassive black hole. The environment is extreme. Radiation levels are high. Gravitational forces are strong. Magnetic fields twist through the region. Forming stars here is different from forming stars in quieter parts of the galaxy. The image suggests more massive stars might form near the galactic center than in the outer regions. The conditions favor giants over dwarfs. If confirmed, this finding would change our understanding of how star populations vary across the Milky Way. Webb gave us the data. Now comes the work of interpretation. And there is much more to interpret, because the center of the galaxy holds not just young stars being born, but ancient stars that have burned for billions of years. Look at any spiral galaxy from the side and you will see a shape like a fried egg. A flat disk spreading outward, a thick bulge rising from the center. Our galaxy has that same structure. The central bulge is a dense ball of stars surrounding the supermassive black hole. And unlike the young, hot stars forming in the nurseries nearby, most stars here are ancient. Some have burned for over 10 billion years. They formed when the universe was young, when the Milky Way itself was still taking shape, when the elements heavier than hydrogen and helium were far less common than they are today. These old stars carry the chemical fingerprints of their era. Astronomers can analyze the light from stars and determine what elements they contain. Stars born in the early universe have fewer heavy elements. Stars born later, from gas enriched by previous generations of supernovas, have more. The bulge contains both types, a mix of ancient metal-poor stars and younger, metal-rich ones. This mixture tells the story of how the galaxy grew over time. Here is where James Webb contributes something new. Previous telescopes struggled to study individual stars in the bulge. The crowding is intense. Dust obscures the view. Distinguishing one star from its neighbors required resolution that older instruments could not provide. Webb's infrared vision cuts through these obstacles. Astronomers can now measure the properties of individual stars near the galactic center with unprecedented precision. They can sort the population by age and composition. They can map how the bulge assembled over cosmic time. Early results reveal complexity. The bulge did not form all at once. It grew through mergers with smaller galaxies that fell into the Milky Way's gravitational embrace. Each merger added stars with different characteristics. The layers of history are preserved in the stellar population like geological strata in rock. Some theories suggest the bulge formed quickly, in a burst of star formation, when the universe was less than 2 billion years old. Other theories propose a slower buildup, with stars accumulating gradually over many billions of years. The truth appears to involve both processes. A rapid early phase created the core of the bulge. Subsequent mergers and internal evolution added to it over time. The bar structure cutting through the center stirred the population, mixing stars from different origins. Understanding the bulge matters because it anchors the galaxy. The gravitational pull of those billions of stars influences the orbits of everything farther out. The spiral arms, the disk, the halo, all respond to the mass concentrated at the center. The bulge is not just a collection of old stars. It is the gravitational heart of the Milky Way. But surrounding that ancient heart, dynamic structures reshape the galaxy even now. Spiral arms sweep through the disk, carrying waves of creation and destruction. From above, the Milky Way would look like a cosmic pinwheel. Bright arms spiraling outward from a central bar, lanes of glowing gas and young stars tracing the curves. Dark dust threading between the light. This is not just beautiful, it is functional. The spiral arms are where most new stars in the galaxy are born. Gas and dust accumulate in these regions, compressed by density waves that sweep through the disk. As material piles up, gravity takes over. Pockets collapse, temperatures rise, fusion ignites. New stars blaze to life in the arms and then drift away over millions of years, leaving room for the next generation. James Webb observed this process in 19 nearby spiral galaxies, revealing structures at the smallest scales ever seen outside our own Milky Way. The images show the architecture of star formation in stunning detail. Filaments of glowing dust trace the arms like veins in a leaf. Bubbles carved by stellar winds and supernovas punctuate the patterns. Bright knots mark regions where dozens or hundreds of stars are forming simultaneously. These findings apply directly to understanding our home. The Milky Way has 4 major spiral arms. 2 are prominent and 2 are less defined. Our solar system sits in one of the smaller structures called the Orion Arm, nestled between the larger Sagittarius and Perseus arms. The arms are not solid structures. Stars and gas pass through them, like cars moving through a traffic jam. The arms themselves are density waves, regions where material temporarily bunches together before spreading out again. This is a confirmed model, supported by decades of observation and simulation. Here is why this matters for life. The compression that triggers star formation also creates the heavy elements necessary for rocky planets. Carbon, oxygen, silicon, iron, all forged in stellar cores and scattered by explosions. Spiral arms concentrate this material. Planets forming in the aftermath of arm passage inherit a rich supply of elements. Worlds like Earth, with iron cores and silicate mantles and atmospheres of nitrogen and oxygen, arise from this cosmic enrichment. Webb's observations of other galaxies show that star formation follows predictable patterns in the arms. The youngest, Most massive stars appear at the leading edges of the arms, where compression is strongest. Older stars trail behind, having drifted since their formation. This gradient reveals the direction the arms rotate and the timescales involved. Our galaxy displays similar structure. Mapping it from the inside is harder than studying face-on spirals from outside, but radio telescopes, infrared surveys, and now Webb data are gradually filling in the picture. The spiral arms breathe. They inhale gas and exhale stars. They pulse with cycles of creation and destruction, and they have been doing so for billions of years, continuously renewing the galaxy even as ancient stars fade. But the disk that holds these arms is not flat. It bends and warps in ways that puzzled astronomers for decades, and a hidden force might be responsible. Our galaxy is twisted. If you could see the Milky Way from the outside, edge-on, you would notice something strange. The disk does not lie flat. The edges bend. One side tilts upward while the other dips down. The shape resembles a vinyl record left in the heat, warped and wavy. This is not new knowledge. Astronomers detected the warping in the 1950s through radio observations of hydrogen gas. What remained unknown was why. Several theories competed for decades. Maybe gravitational interactions with satellite galaxies tugged the disk out of shape. Maybe magnetic fields exerted torques on the outer regions. Maybe some long-ago collision left permanent scars. Recent research points to a different culprit: dark matter. The invisible substance that makes up most of the mass in the universe appears to form a halo around the Milky Way. This halo is not perfectly spherical and not perfectly aligned with the disk. The misalignment creates gravitational torques. Imagine spinning a top on a tilted surface. The tilt pulls on the top, causing it to wobble. Something similar may be happening to our galaxy. The dark matter halo tugs on the disk, warping it over time. This explanation remains a theory, but mounting evidence supports it. Data from the Gaia Space Telescope revealed that stars in the outer disk move in patterns consistent with a warped structure influenced by an asymmetric halo. Computer simulations reproduce the observed shape when they include a tilted dark matter distribution. Here is where it gets more unsettling. The warping is not static, it precesses. The twisted regions rotate around the galaxy like a slow-motion wave. The precession period is estimated at hundreds of millions of years. Over time, the warp sweeps through the entire disk, bending different regions as it passes. You are living on a galaxy that wobbles. James Webb contributes to this research by studying the stars in the outer disk with greater precision. Infrared observations reach stars that optical telescopes cannot see, filling gaps in the map of the galactic edge. The more complete the map, the better astronomers can model the dark matter distribution. And here is the truly humbling part. The visible galaxy, all the stars and gas and dust that telescopes can detect, represents only a small fraction of the total mass. The dark matter halo extends far beyond the disk. Estimates suggest it could reach nearly 2 million light-years in diameter. The part of the Milky Way you can see is like the glowing tip of an iceberg. Most of the mass is invisible, detectable only through its gravitational effects on things we can observe. That invisible mass holds the galaxy together. Without it, the stars would fly apart, the disk would dissolve, the spiral arms would unwind into chaos. Dark matter is the skeleton on which everything visible hangs, and astronomers are only beginning to understand its shape. You cannot see most of the Milky Way. This sounds strange. Look up at the night sky, and the galaxy seems to reveal itself in that glowing band of light. Stars beyond counting, clouds of gas lit by stellar radiation, the visible machinery of a vast cosmic structure. But all of that represents perhaps 15% of the total mass. The rest is dark matter. It does not emit light. It does not absorb light. It passes through ordinary matter like a ghost walking through walls. The only way we know it exists is through gravity, and its gravity is enormous. The dark matter halo surrounding the Milky Way extends far beyond the visible disk. Current estimates suggest it reaches between 1 and 2 million light-years in diameter. The visible galaxy, stretching roughly 100 to 200,000 light-years, sits at the center of this invisible ocean. How do astronomers know this? They measure the speeds of objects at the edges of the galaxy: stars, gas clouds, satellite galaxies. According to the laws of gravity, objects farther from the center should orbit more slowly. This is how planets behave around our star. Mercury moves fast, Neptune moves slow, but galaxies do not follow that pattern. The outer regions of the Milky Way move almost as fast as the inner regions. Something provides extra gravitational pull at large distances. That something must be massive, widespread, and invisible. Dark matter. The concept has been tested for nearly a century. Alternative theories have been proposed and mostly rejected. The evidence from multiple independent observations points consistently toward the same conclusion. There is more matter out there than we can see. James Webb contributes indirectly to this research. By studying galaxies at various distances and ages, astronomers can track how dark matter halos evolve over cosmic time. Early galaxies appear to have different dark matter distributions than modern ones. Mergers and accretion reshape the halos as galaxies grow. Our own halo carries the scars of past encounters. Dwarf galaxies that fell into the Milky Way left streams of stars behind them. These streams trace the orbits of the destroyed satellites, revealing the shape of the dark matter they passed through. Here is something that should make you pause. Right now, dark matter particles are passing through your body, billions of them every second. They interact so weakly with ordinary matter that you will never notice. Detectors buried deep underground occasionally register a collision, maybe. The signals remain uncertain. The most common substance in the universe remains the most mysterious. We know it has mass. We know it clumps together under gravity. We know it shaped the formation of galaxies and continues to influence their evolution. We do not know what it is. Solving that mystery would rank among the greatest achievements in the history of science, and the Milky Way, our home, is one of the best laboratories for studying it. But dark matter is not the only invisible feature of our galaxy. The dimensions of the visible structure itself hide surprises. The Milky Way is wide, 100,000 to 200,000 light-years across, depending on where you draw the boundary. A span so vast that light itself needs a significant fraction of a million years to cross it. But here is something most people do not realize. The galaxy is thin. Compared to its width, the disk of the Milky Way is remarkably flat, only about 1,000 light-years from top to bottom in most regions. Some areas are thicker, some are thinner, but on average, the ratio of width to height is about 100 to 1. Imagine a dinner plate. Now imagine that plate is 200 feet wide. That is roughly the proportion of the Milky Way. Why so flat? It comes down to physics and time. When the galaxy formed billions of years ago, it started as a chaotic cloud of gas. Material fell inward under gravity from all directions. But as the cloud rotated, conservation of angular momentum took over. Material moving in the plane of rotation could settle into stable orbits. Material moving perpendicular to that plane collided with other particles, lost energy, and eventually joined the disk. Over millions of years, the random motions averaged out. The cloud collapsed into a spinning disk. Stars formed within that disk and inherited its flat geometry. This process is confirmed by observations of galaxy formation throughout the universe. James Webb has captured images of young galaxies still assembling, their shapes irregular and blobby. As they age, they flatten. Rotation imposes order on chaos. Our galaxy completed this process long ago. The thin disk contains most of the young stars, the spiral arms, and the gas clouds where new stars form. It is the active, dynamic layer of the Milky Way. But there is more to the structure than just the thin disk. A thick disk surrounds it, This layer contains older stars with more random motions. They orbit the galactic center but also bob up and down, passing through the thin disk on eccentric paths. The thick disk formed earlier, before the galaxy fully settled. Its stars carry the memory of a more chaotic era, and beyond the thick disk lies the halo, a sparse sphere of ancient stars and globular clusters. Some of these objects are among the oldest in the universe, forming over 13 billion years ago. They orbit the galaxy on long, looping trajectories that take them far above and below the plane. The architecture of the Milky Way preserves its history in layers: thin disk, thick disk, halo. Each layer represents a different epoch, a different stage of assembly. Webb helps astronomers study these layers by resolving individual stars at greater distances than ever before. Each star is a data point in the reconstruction of how our galaxy came to be. But one structure cuts across these layers, defying the neat categories: a bar of stars and gas that channels material toward the center. The Milky Way is not a simple spiral. At its center, a bar of stars cuts through the disk. This structure stretches roughly 25,000 light-years from end to end, passing through the galactic core and connecting opposite sides of the inner galaxy. Bars are common in spiral galaxies. About 2/3 of spirals in the nearby universe have them. But for a long time, astronomers were not sure whether the Milky Way belonged to that majority. Seeing the bar from inside is difficult. Dust obscures the view. Distance complicates measurements. The structure is edge-on from our perspective, making it hard to distinguish from the surrounding bulge. Infrared surveys eventually confirmed the bar's existence. By mapping the distribution of red giant stars, which are bright in infrared light, astronomers traced a distinct, elongated structure oriented at an angle to our line of sight. The bar was real. James Webb adds new detail to this picture. High-resolution infrared images reveal the stars within the bar region with greater clarity. Measurements of stellar motions show how material flows along the bar and toward the center. Here is why the bar matters. It acts as a funnel. Gas in the inner disk does not orbit in perfect circles. The gravitational influence of the bar disturbs those orbits. Gas loses angular momentum and spirals inward along the bar toward the central regions. This inflow feeds the supermassive black hole. Not all the gas falls into Sagittarius A. Much of it accumulates in a ring around the center, fueling intense star formation. The Sagittarius B2 and Sagittarius C regions discussed earlier sit in this central zone, enriched by material that the bar has channeled inward. The bar also influences the spiral arms. Where the bar ends, the arms begin. The transition zones show complex dynamics as gas switches from bar-following orbits to arm-following orbits. Shocks and compressions trigger star formation at these junctions. Our own position in the Orion arm may have been influenced by the bar. Over billions of years, the gravitational effects of the bar have redistributed stars throughout the disk. The Milky Way's structure today reflects the cumulative effect of the bar stirring the galactic pot. Here is something to consider. Bars are not permanent. Simulations suggest they can form, dissolve, and reform over the lifetime of a galaxy. Interactions with satellite galaxies can strengthen or weaken them. The bar we see today might not have existed a few billion years ago. It might not exist a few billion years from now. The galaxy is always changing. The structure you see in images is a snapshot of a dynamic system. The bar channels material. Star formation consumes it. New generations replace old. The cycle continues. And that cycle has been running for a very long time. Longer, perhaps, than you might have guessed. The Milky Way is ancient. Some of the stars in the galactic halo formed over 13 billion years ago. That means they ignited when the universe itself was only a few 100 million years old, barely a cosmic infant. Think about what that implies. The raw material of our galaxy was already gathering before most other galaxies had finished forming, before the first planets. before the first heavy elements had been synthesized in significant quantities. The oldest stars carry proof of their age. They contain almost no elements heavier than hydrogen and helium. These metals, as astronomers call them, are forged inside stars and scattered when those stars explode. Early generations had no previous explosions to draw from. They formed from nearly pure primordial gas. James Webb has observed some of the earliest galaxies in the universe, pushing back the timeline of cosmic structure formation. What it found surprised everyone. Galaxies existed earlier than models predicted. Structures that should have taken billions of years to assemble appeared within a few 100 million years of the Big Bang. Some of these early galaxies already showed spiral arms. Some contained supermassive black holes. Our Milky Way fits into this picture as one of the early arrivals. Not the first generation, but close. The galaxy began assembling when the universe was less than 1 billion years old. Over the following 13 billion years, it grew through accretion and mergers, swallowing smaller galaxies and accumulating mass. Here is something confirmed by recent research. Nearly half the matter in the Milky Way may have originated outside it. Gas expelled from distant galaxies drifted through intergalactic space for billions of years before falling into our gravitational embrace. Stars formed elsewhere were captured during mergers. The Milky Way is not a closed system. It is a collector. This ongoing assembly continues today. Streams of stars from disrupted dwarf galaxies thread through the halo. Gas falls inward from the surrounding medium. The Magellanic Clouds, our largest satellite galaxies, are slowly being torn apart by tidal forces. In a few billion years, their remnants will merge with us. The age of the Milky Way is not a single number. Different components have different ages. The halo is oldest. The thick disk came next. The thin disk is younger, continuously renewed by star formation. The spiral arms contain the youngest stars of all. You live in a galaxy with parts older than most things in the universe, and parts that formed just yesterday, cosmically speaking. That range of ages, from 13 billion years to mere millions, coexists in one structure, one home, one island in the vast ocean of space. But this island is not standing still. It moves, and it carries you with it at speeds that defy comprehension. Sit very still. Feel motionless? You are not. At this exact moment, you are hurtling through space at a speed so fast that your mind cannot truly grasp it. Start with Earth's rotation. If you stand at the equator, the planet's spin carries you eastward at about 1,000 miles per hour. You do not feel it because everything around you moves at the same speed. The air, the buildings, the ground beneath your feet. Now add Earth's orbit around our star. Our planet traces an elliptical path roughly 93 million miles in circumference. It completes one lap every year, which works out to about 67,000 miles per hour. Every hour, you cover a distance greater than the circumference of Earth itself. But we are just getting started. Our entire solar system orbits the center of the Milky Way. This motion is much faster. The current best estimates place the speed at roughly 500,000 miles per hour. Some measurements suggest slightly higher or lower values, but all agree on the general magnitude. 500,000 miles every 60 minutes. At that rate, you travel farther in a single day than most spacecraft have traveled in their entire missions. This motion has a name. Astronomers call it the galactic orbital velocity. The path is not circular. It is slightly elliptical, wobbling up and down through the galactic plane as it goes. The orbit takes approximately 230 million years to complete. One full loop around the galaxy. One galactic year. Here is some perspective. The last time our solar system was in this exact position, dinosaurs were just beginning to appear on Earth. The Atlantic Ocean did not exist. The continents were joined in a single landmass. Life on our planet was unrecognizably different. The next time we return here, evolution will have transformed everything again. But the motion does not stop at the galactic orbit. The entire Milky Way is moving through space. Our galaxy travels toward a region called the Great Attractor, a concentration of mass that pulls on everything in our cosmic neighborhood. This motion adds another component to our velocity. And on top of that, the universe itself is expanding, carrying galaxies apart from one another. You are layered in motions, spinning on a rotating planet, orbiting a star, orbiting a galaxy, falling toward distant gravitational wells, expanding with the fabric of space, all of it happening simultaneously, all of it imperceptible. This motion shaped the Milky Way. Collisions and mergers occurred because galaxies crossed paths. Star formation happened because gas compressed during orbital dynamics. The structures you see in images result from billions of years of movement, and that movement will determine the future, because another galaxy is coming. And it is coming fast. The Milky Way should not have existed so early. At least, that is what astronomers believed. Spiral galaxies with defined arms and flat disks were supposed to take billions of years to form. The early universe was too chaotic, too violent, too full of mergers and collisions for such delicate structures to survive. James Webb proved them wrong. The telescope has detected spiral galaxies existing when the universe was only 1 to 2 billion years old, structures resembling our own Milky Way, complete with spiral arms and organized disks, appearing far earlier than any model predicted. This is confirmed by multiple research teams using Webb data. One discovery particularly stunned the scientific community. A galaxy nicknamed Alaknanda, located about 12 billion light-years away, shows a well-defined spiral structure. It formed when the universe was just 1.5 billion years old, a mere fraction of its current age. Alaknanda spans about 32,000 light-years. Its two spiral arms wind smoothly around a central disk. New stars form along the arms at a rate dozens of times faster than in the modern Milky Way. This galaxy looks like a younger, smaller version of our home. The discovery challenges fundamental theories about galaxy formation. Standard models predicted that early galaxies would be messy, irregular blobs, chaotic clumps, distorted shapes from constant collisions. The gravitational settling needed to form flat disks and spiral arms was supposed to take many billions of years. Alaknanda took a shortcut. Somehow, it assembled a spiral structure in less than 2 billion years. The gas settled into a disk. The arms developed. Star formation organized itself along the spiral patterns. All of this happened while most of the universe was still a turbulent fog of merging protogalaxies. Astronomers are still working to explain how. One possibility involves the dark matter halos. If the halo forms quickly enough and has the right shape, it might allow the gas to settle rapidly. The gravitational well provides stability. The disk forms faster than expected. Another possibility involves feedback from early black holes. Energy from supermassive black holes might clear out turbulent gas, allowing the remaining material to organize itself more efficiently. Both explanations remain theories under investigation. Here is what this means for understanding our own galaxy. The Milky Way's structure might have appeared earlier than we thought. The spiral arms might be older. The disk might have formed faster. Our home might be more ancient in its recognizable form than previous models suggested. Webb is also finding Milky Way twins at closer distances. Over 1,000 disk galaxies have been identified in the early universe, swarming through an era when they supposedly could not exist. The exceptions have become the rule. Galaxies like ours are not rare latecomers. They are common throughout cosmic history, emerging quickly and persisting for billions of years. But while some galaxies resemble the Milky Way, one discovery revealed a galaxy that might literally be us, a baby version of our home caught in the act of forming. Imagine looking through a time machine, not at distant stars or ancient light, but at your own home as it existed billions of years ago. A glimpse of the Milky Way in its infancy, still assembling, still growing, still finding its shape. James Webb found exactly that. A galaxy nicknamed the Firefly Sparkle appeared in Webb's Deep Field observations. It exists about 600 million years after the Big Bang, making it one of the earliest structures ever detected in such detail. But the truly remarkable part is not its age, it is its mass. The Firefly Sparkle weighs approximately the same as the Milky Way would have weighed at the same stage of development. If you could rewind cosmic time and watch our galaxy forming, it might have looked almost identical to this distant object. This is confirmed science, published in the journal Nature. The galaxy gleams with 10 distinct star clusters, each one visible thanks to gravitational lensing. A massive foreground galaxy cluster bent and magnified the light from Firefly Sparkle, acting like a cosmic telescope that boosted Webb's already extraordinary vision. Without that natural magnification, the galaxy would have been invisible. The star clusters reveal a galaxy in the process of active assembly. Material is falling inward, stars are igniting in bursts. The structure is chaotic but organized, showing the earliest signs of the disk that will eventually form. Here is what makes this discovery profound. Astronomers have studied the Milky Way for centuries. They have mapped its stars, measured its motions, analyzed its chemistry, but they could never see what it looked like in the beginning. Now they can. The Firefly Sparkle provides a template, a snapshot of what a Milky Way progenitor actually looked like during the universe's first billion years. The data will constrain models of galaxy formation, ruling out scenarios that cannot produce this observed structure. The galaxy is not alone in its region of space. Webb detected 2 companion galaxies within close proximity. One sits only 6,500 light-years away. The other is separated by about 42,000 light-years. For context, the modern Milky Way spans 100,000 light-years. All 3 would fit inside our galaxy with room to spare. These companions might eventually merge with the Firefly Sparkle, adding their mass to the growing structure. Or they might drift apart, becoming separate galaxies with their own destinies. The future is unwritten, but the past is now visible in ways it never was before. Every galaxy has an origin story. Ours began in conditions similar to what Webb captured in that distant field. A small collection of gas and stars, gathering material, forming clusters, slowly building toward the spiral giant we inhabit today. The Firefly Sparkle is a mirror across time, and looking into that mirror, astronomers are seeing something familiar, something that feels like home. But while we gaze at our past, another galaxy is charging toward our future, and it is far closer than the Firefly Sparkle ever was. 2.5 million light-years away, a monster approaches. The Andromeda Galaxy, also known as Messier 31, the nearest large galaxy to the Milky Way and the most distant object visible to the naked eye on a clear, dark night. It is heading straight for us. Andromeda moves through space at approximately 250,000 miles per hour relative to the Milky Way. That sounds terrifyingly fast, and it is. But the distances involved are so vast that the approach will take billions of years. For over a century, astronomers knew Andromeda was coming closer. The light from the galaxy shows a blue shift, meaning its wavelengths are compressed toward the blue end of the spectrum. This happens when a light source approaches the observer. Every measurement confirmed the same conclusion. Andromeda is falling toward us. In 2012, researchers used the Hubble Space Telescope to measure the sideways motion of Andromeda with unprecedented precision. They tracked the positions of stars over several years, comparing them against distant background galaxies that served as fixed reference points. The results seemed definitive. The 2 galaxies would collide in approximately 4 billion years. But science updates itself when new data arrives. A 2025 study using both Hubble and Gaia data complicated the picture. The researchers ran hundreds of computer simulations incorporating the latest measurements of positions, velocities, and masses. The conclusion shifted. There is now approximately a 50-50 chance of a collision within the next 10 billion years. The certainty evaporated. The outcome became uncertain. What changed? 2 factors emerged as critical. First, the Large Magellanic Cloud, a satellite galaxy of the Milky Way, exerts gravitational influence on our galaxy's trajectory. It pulls the Milky Way slightly off course, potentially deflecting us away from a direct collision path. Second, the Triangulum Galaxy, a smaller spiral that accompanies Andromeda, adds complexity to the gravitational dynamics. Its presence makes the system harder to predict. Here is what remains certain. The Milky Way and Andromeda are gravitationally bound. They belong to the same local group of galaxies. Even if they miss on the first pass, they will eventually merge. The question is, when, not if. Some simulations show a near miss followed by a long orbital dance before eventual merger. Others show a direct collision in 4 to 5 billion years. A small percentage show the galaxies passing close enough to distort each other but remaining separate for tens of billions of years. The fate of our galaxy is genuinely uncertain. This might feel unsettling, or it might feel liberating. The future is not fixed. Even on the largest scales, the universe contains surprises. But whether the collision happens in 4 billion years or 10 billion years, the outcome will be spectacular and terrifying. Picture two cities walking toward each other. Millions of buildings, countless streets, infrastructure stretching for miles in every direction. Now picture them passing through each other without a single collision. That is what happens when galaxies merge. The Milky Way contains between 100 billion and 400 billion stars. Andromeda contains roughly 1 trillion. When these two giants finally meet, the total number of stars involved will approach 1.5 trillion, yet almost none of them will collide. This sounds impossible. How can trillions of objects pass through each other without contact? The answer is distance. Stars are unimaginably far apart relative to their sizes. The nearest star to our solar system, Proxima Centauri, sits about 4 light-years away. If our star were the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball located nearly 700 miles away. Now multiply that emptiness by hundreds of billions. Even in the densest regions of each galaxy, the average spacing between stars exceeds 100 billion miles. When the galaxies merge, stars will pass by each other like ships in an infinite ocean. Close approaches will be rare. Actual collisions will be almost non-existent, but the galaxies themselves will be destroyed, not by impacts, by gravity. As Andromeda and the Milky Way approach, tidal forces will begin distorting both structures. Spiral arms will stretch, disks will warp, stars will be flung onto new orbits, some ejected entirely into intergalactic space. The first close pass will trigger chaos. Gas clouds will collide, even though stars will not. When gas meets gas, it compresses. Compression triggers star formation. The sky will blaze with new stars igniting by the millions. Simulations show the night sky during this period would look nothing like today. Brilliant nebulae would glow across the heavens. New stars would appear faster than astronomers could catalogue them. The Milky Way's familiar band would distort into unrecognizable shapes. After the first pass, the galaxies will swing apart, but not for long. Gravitational attraction will pull them back together. A second pass will follow, then a third. Each encounter will strip away more structure, blend more populations, erase more of the original identities. Over approximately 2 billion years, the two spirals will merge into one. The final product will look nothing like either parent. The spiral arms will dissolve. The flat disks will puff into a spherical blob. The organized rotation will become random motion in all directions. A new type of galaxy will emerge, and it already has a name. Some astronomers prefer Milkdromeda. Others suggest different names entirely, but the concept remains the same. Billions of years from now, the Milky Way and Andromeda will cease to exist as separate entities. One merged galaxy will take their place. The structure will likely be an elliptical galaxy, a giant spheroid of stars with no spiral arms, no flat disk, no organized rotation. The graceful pinwheel patterns of both parent galaxies will be gone. This is confirmed by computer simulations run by multiple research teams. Elliptical galaxies are common in the universe. They typically form through mergers of spiral galaxies. The violent gravitational interactions scramble the orderly motions of stars, converting disk rotation into random orbits that fill a three-dimensional volume. Milky Way will be enormous. The combined stellar population will exceed 1 trillion stars. The merged dark matter halos will create a gravitational well deeper than either parent galaxy possessed alone. Satellite galaxies will continue orbiting the new structure, slowly falling inward over billions of years. Here is a detail that might comfort you. Our solar system will probably survive. The chances of another star passing close enough to disrupt planetary orbits are negligible. Earth will continue circling our star as it does today. The constellations will look completely different, but the local neighborhood will remain intact. We might even get a better view. During the merger, our solar system could be flung outward from the galactic center. From a more distant vantage point, future observers might see the entire merged galaxy spread across their sky like a glowing dome, or we might fall inward toward the center. The supermassive black holes at the cores of both galaxies will eventually spiral together. When they merge, they will release gravitational waves powerful enough to ripple through space-time across the universe. The combined black hole will anchor the center of Milky Way, millions of times more massive than any black hole currently in either galaxy. By this time, Earth will be long dead. Our star will have exhausted its hydrogen fuel in about 5 billion years. It will swell into a red giant, potentially engulfing the inner planets. Even if Earth survives that phase, it will become a frozen rock orbiting a fading white dwarf. No humans will witness the final merger unless we leave. The timeline is long enough for a civilization to spread across multiple star systems, to build habitats in distant regions, to watch the collision from safe vantage points scattered throughout the galaxy. The merger is not an ending. It is a transformation. One chapter closing, another opening. But the Milky Way's story does not involve only Andromeda. Dozens of smaller galaxies already orbit us, and their fates are being decided right now. The Milky Way is not alone. More than 50 smaller galaxies orbit our own, bound by gravity into a cosmic family. Some are visible to the naked eye. Others are so faint that only the most sensitive telescopes can detect them. The largest and most famous are the Magellanic Clouds. The Large Magellanic Cloud spans about 14,000 light-years and contains roughly 30 billion stars. Its smaller companion, the Small Magellanic Cloud, is about 7,000 light-years across. Both are visible from the southern hemisphere as fuzzy patches of light detached from the main band of the Milky Way. They are being destroyed. Tidal forces from our galaxy are ripping them apart. Streams of gas and stars trail behind the clouds, stretching across tens of thousands of light-years. This material will eventually fall into the Milky Way, adding to our galaxy's mass. The process takes hundreds of millions of years, but it is happening right now. Every moment, the Magellanic Clouds lose a little more of themselves to the Milky Way's gravitational appetite. James Webb has observed the Magellanic Clouds in unprecedented detail. The telescope detected brown dwarfs, objects too small to sustain hydrogen fusion, in the star cluster NGC 602 within the Small Magellanic Cloud. This marked the first time such faint objects were identified outside our own galaxy. The discovery matters because brown dwarfs reveal information about star formation processes. Finding them in a satellite galaxy shows that similar physics operates in different environments. Beyond the Magellanic Clouds, dozens of dwarf galaxies orbit at various distances. Sagittarius Dwarf Elliptical Galaxy is currently passing through the disk of the Milky Way. It has completed several orbits over billions of years, losing stars with each passage. Streams of its former members now wrap around our galaxy like ribbons around a gift. Ursa Minor Dwarf and Draco Dwarf are ancient systems containing some of the oldest stars known. Their stellar populations formed over 13 billion years ago, preserving chemistry from the early universe. Some satellite galaxies are so faint they were discovered only recently. Ultra-faint dwarfs contain just a few thousand stars spread across regions larger than globular clusters. They are held together by dark matter, their visible components representing a tiny fraction of their total mass. These objects challenge definitions. Where does a galaxy end and a star cluster begin? The distinction blurs at the smallest scales. Astronomers debate classifications, while the objects themselves remain indifferent to human categories. The satellite system preserves the history of galactic assembly. Each dwarf galaxy that fell into the Milky Way left traces. Stellar streams mark their orbits. Chemical signatures identify their former members. The halo of our galaxy is populated by immigrants from consumed satellites. We are cannibals. The Milky Way grew by eating smaller galaxies. It continues eating them today, and it will keep eating until something larger swallows us. But there is a mystery in all this consumption. Something that should be there is missing. Add up everything visible in and around the Milky Way. Stars, gas, dust, planets, black holes, neutron stars, white dwarfs, every form of ordinary matter that telescopes can detect. Now compare that total to what should exist based on cosmological models. Half of it is missing. This is not the dark matter mystery. Dark matter is invisible by nature, detectable only through gravity. The missing matter is ordinary stuff, the same protons and neutrons that make up your body. It should be visible. It should be detectable. But astronomers cannot find it. The discrepancy has puzzled researchers for decades. The standard model of cosmology predicts how much ordinary matter the universe contains based on observations of the cosmic microwave background, the afterglow of the Big Bang. That prediction is precise. Ordinary matter should comprise about 5% of the universe's total energy content. When astronomers count up the matter in galaxies and gas clouds throughout the cosmos, they fall short by roughly half. Where did it go? One possibility is the hot gas halo surrounding galaxies like the Milky Way. Gas at temperatures of millions of degrees emits X-rays rather than visible light. This hot halo is difficult to observe, requiring specialized telescopes sensitive to high-energy radiation. Recent studies suggest the Milky Way's halo might contain enough hot gas to account for the missing matter. If confirmed, this would mean the visible galaxy is surrounded by an envelope of superheated gas extending hundreds of thousands of light-years. The mass of this halo might equal or exceed the mass of all the stars in the disk. James Webb contributes indirectly to this research. By studying other galaxies in infrared light, astronomers can map the relationship between visible matter and surrounding halos. Patterns observed in external galaxies help constrain models of our own. Here is what makes this mystery important. The missing baryons, as astronomers call them, influence galaxy evolution. Gas that falls into galaxies fuels star formation. Gas that gets heated and expelled removes that fuel. The balance between inflow and outflow determines how many stars a galaxy can make. Understanding where the matter went means understanding how galaxies work. Some models suggest the missing matter was blown out of galaxies by supernova explosions and black hole activity. This feedback heated the gas, preventing it from cooling and collapsing into stars. Other models suggest the matter never fell into galaxies at all. It might reside in filaments between galaxies, part of the cosmic web that connects structures across the universe. The Milky Way is a laboratory. Add up everything visible in and around the Milky Way. Stars, gas, dust, planets, black holes, neutron stars, white dwarfs, every form of ordinary matter that telescopes can detect. Now compare that total to what should exist based on cosmological models. Half of it is missing. This is not the dark matter mystery. Dark matter is invisible by nature, detectable only through gravity. The missing matter is ordinary stuff, the same protons and neutrons that make up your body. It should be visible. It should be detectable. But astronomers cannot find it. The discrepancy has puzzled researchers for decades. The standard model of cosmology predicts how much ordinary matter the universe contains based on observations of the cosmic microwave background, the afterglow of the Big Bang. That prediction is precise. Ordinary matter should comprise about 5% of the universe's total energy content. When astronomers count up the matter in galaxies and gas clouds throughout the cosmos, they fall short by roughly half. Where did it go? One possibility is the hot gas halo surrounding galaxies like the Milky Way. Gas at temperatures of millions of degrees emits X-rays rather than visible light. This hot halo is difficult to observe, requiring specialized telescopes sensitive to high-energy radiation. Recent studies suggest the Milky Way's halo might contain enough hot gas to account for the missing matter. If confirmed, this would mean the visible galaxy is surrounded by an envelope of superheated gas extending hundreds of thousands of light-years. The mass of this halo might equal or exceed the mass of all the stars in the disk. James Webb contributes indirectly to this research. By studying other galaxies in infrared light, astronomers can map the relationship between visible matter and surrounding halos. Patterns observed in external galaxies help constrain models of our own. Here is what makes this mystery important. The missing baryons, as astronomers call them, influence galaxy evolution. Gas that falls into galaxies fuels star formation. Gas that gets heated and expelled removes that fuel. The balance between infall and outflow determines how many stars a galaxy can make. Understanding where the matter went means understanding how galaxies work. Some models suggest the missing matter was blown out of galaxies by supernova explosions and black hole activity. This feedback heated the gas, preventing it from cooling and collapsing into stars. Other models suggest the matter never fell into galaxies at all. It might reside in filaments between galaxies, part of the cosmic web that connects structures across the universe. The Milky Way is a laboratory for testing these ideas. Its halo can be probed in ways that distant galaxies cannot. Absorption lines in the spectra of background quasars reveal gas along the line of sight. X-ray observations map the hot component. Radio telescopes trace cooler clouds. Piece by piece, the inventory grows, but the final accounting remains incomplete. Somewhere, vast quantities of ordinary matter hide in forms we have not yet learned to see. The missing matter represents one frontier of ignorance. Another frontier involves something even more mysterious. A strange glow from the galactic center that might finally reveal what dark matter actually is, and if confirmed, it would be the discovery of the century. Something glows at the center of the Milky Way, not the stars, not the gas, not the supermassive black hole and its flaring accretion disk. Something else. For over a decade, NASA's Fermi Gamma Ray Space Telescope has detected an excess of gamma rays coming from the galactic center. The signal forms a halo-like structure, roughly spherical, centered on Sagittarius A. This excess does not match any known source. Pulsars, the rapidly spinning remnants of dead stars, produce gamma rays, but models struggle to account for enough pulsars in the right distribution to explain the observed glow. The signal is too smooth, too extended, too symmetric. One possibility has electrified the physics community: dark matter annihilation. If dark matter consists of particles that can collide and destroy each other, those collisions would release energy. That energy would include gamma rays at specific wavelengths determined by the mass of the particles. The Fermi excess matches predictions for a type of dark matter called WIMPs, weakly interacting massive particles. This remains a theory under intense scrutiny. A 2025 study reanalyzed 15 years of Fermi data using updated models of the Milky Way's structure. The researchers accounted for the galaxy's complex history, including past mergers that would have shaped the dark matter distribution. Their conclusion grabbed headlines. The gamma-ray signal matches the expected shape of a dark matter halo far better than previous analyses suggested. The flattened, egg-like distribution of the signal corresponds to what simulations predict for a halo shaped by the Milky Way's gravitational history. Dark matter and pulsars remain essentially indistinguishable with current data, but the door has opened wider. If WIMPs are real, and if they produce the Fermi excess, then scientists have already detected dark matter indirectly. The invisible substance that holds galaxies together would finally have an observable signature. Confirmation requires more evidence. The Cherenkov Telescope Array, currently under construction in Chile and Spain, will scan the galactic center with unprecedented sensitivity. It should detect gamma rays at energies that could distinguish between dark matter and pulsars. Results are expected by the late 2020s. Here's what this means for understanding the Milky Way. The dark matter halo is not just a gravitational scaffolding. It might be an active participant in the galaxy's energy budget. Collisions at the center might inject gamma rays continuously, a slow burn that has lasted billions of years. The galaxy glows in ways we never imagined. Visible light shows stars. Infrared reveals dust and forming stars. Radio waves trace gas. X-rays illuminate hot halos and violent explosions. And gamma rays might finally show us the invisible skeleton holding everything together. The Milky Way hides secrets in every wavelength. James Webb has revealed many of them, but even Webb cannot see gamma rays. What it can see, however, has transformed our understanding of everything else. Before James Webb, astronomers looked at the universe through foggy glass. Visible light telescopes showed spectacular images, but dust blocked the view of countless regions. The centers of galaxies remained obscured. Star-forming clouds hid their contents. The earliest epochs of cosmic history faded into darkness. Webb sees through the fog. Infrared light passes through dust that visible light cannot penetrate. Wavelengths that get absorbed and scattered in the visible spectrum sail cleanly through dense clouds. Regions that appeared as black voids now glow with activity. The galactic center is the most dramatic example. For decades, astronomers knew that something extraordinary existed at the heart of the Milky Way. Radio telescopes detected signals. X-ray satellites glimpsed high-energy processes, but the visible light images showed only a murky darkness where dust blocked the view. Webb revealed 500,000 stars in a single frame of Sagittarius C. That image alone contained more detailed information about the galactic center than all previous visible light observations combined. Features that astronomers theorized about became directly observable. Structures that existed only in models appeared on screens. The telescope also sees farther back in time than any predecessor. Light from the early universe has been stretched by cosmic expansion. Wavelengths that started as visible or ultraviolet light arrive at Earth as infrared. Webb's instruments are optimized for exactly these wavelengths. Galaxies from the first billion years after the Big Bang now appear in sharp detail. The fireflies sparkle, Alaknanda, thousands of early structures that challenge formation theories. Webb has rewritten the timeline of cosmic assembly, showing that organization emerged far faster than anyone expected. Closer to home, Webb studies planets and moons in our own solar system. Atmospheres reveal their chemistry. Surfaces show their geology. Even objects in the outer reaches, cold and faint, become visible in infrared. But the Milky Way benefits most from Webb's capabilities. Every star-forming region can now be studied in detail. The chemistry of stellar nurseries reveals what elements will become available for planet formation. The distribution of young stars shows how galactic structure influences where new worlds can arise. Webb observed the most massive star-forming cloud in the galaxy. Sagittarius B2 appeared in full glory, its hundreds of massive stars glowing through the dust. Protostars still gathering mass became visible as bright red points at the tips of gas pillars. The telescope also captured the black hole's tantrums. 48 hours of observations revealed the constant flaring from Sagittarius A, activity that previous instruments could only glimpse in brief snapshots. Webb does not just take pretty pictures. It gathers spectra, splitting light into component wavelengths that reveal chemical composition, temperature, motion, and distance. Every observation generates data that will fuel research for years. The Milky Way we thought we knew was a rough sketch. Webb is filling in the details, pixel by pixel, spectrum by spectrum, revelation by revelation. And what those details reveal changes the biggest question of all, the one that keeps people staring at the night sky and wondering. You exist on one planet, orbiting one star among hundreds of billions. That star sits in one galaxy among trillions. That galaxy spans distances so vast that light needs tens of thousands of years to cross it. And beyond its visible edge, invisible matter extends for millions of light years more. The scale is crushing. It can make human concerns seem insignificant. Wars and politics and daily struggles shrink to nothing against the backdrop of cosmic immensity. But there is another way to see it. Everything that makes you possible came from this galaxy. The hydrogen in your body formed in the Big Bang itself. The carbon and oxygen came from dying stars that scattered their ashes across the Milky Way billions of years ago. The iron in your blood was forged in supernova explosions more violent than anything you can imagine. You are not separate from the galaxy. You are made of it. James Webb is showing that the conditions for life might be far more common than previous generations dared to hope. Every star-forming region Webb observes contains the chemical signatures of complex molecules, carbon chains, oxygen compounds, nitrogen-bearing structures. The building blocks of biology appear wherever new stars ignite. In 2025, researchers used Webb to detect 5 complex organic molecules in ice around a star outside the Milky Way entirely: methanol, acetaldehyde, ethanol, methyl formate, acetic acid. The ingredients for life exist even beyond our galaxy. Closer to home, the Milky Way contains somewhere between 100 billion and 400 billion planets. Statistical analysis of Kepler data suggests rocky worlds in habitable zones are common. Perhaps 1 in 5 stars hosts an Earth-sized planet where liquid water could exist. That means billions of potential homes in our galaxy alone. We do not know if any of them host life. The chemistry is there. The conditions seem right. But biology requires something more, a spark that transforms dead molecules into living systems. We do not understand that transition well enough to predict where it happens. What we do know is that the search has never been more promising. Webb can analyze the atmospheres of exoplanets, looking for signatures that might indicate biological activity: oxygen, methane, ozone, combinations of gases that should not coexist without something actively producing them. The first hints might come within years, or decades, or never, but the possibility exists in a way it did not before. Here is what the Milky Way teaches us. The universe is not hostile to life. It produces the elements life needs. It creates environments where those elements can combine. It operates by laws that permit complexity to arise from simplicity. We are proof that it happens at least once. The question is whether once is a miracle or a pattern. James Webb cannot answer that question alone. But every observation narrows the possibilities. Every discovery refines the estimates. Every image of a star-forming cloud or an ancient galaxy or a planet's atmosphere adds another data point. The Milky Way raised you. Its physics created your atoms. Its processes delivered them to the cloud that became our solar system. Its structure placed Earth in a zone where life could persist for billions of years. You are the galaxy looking back at itself, wondering, questioning, searching, and for the first time in human history, the tools exist to find answers. The true scale of the Milky Way is not just about size. It is about possibility, about connection, about the extraordinary fact that matter can arrange itself into forms that contemplate their own existence. Look up tonight. That faint band of light holds more secrets than any generation has ever uncovered, and we are only beginning. Stars do not live forever. They burn through their fuel, exhaust their energy, and die. But death in the cosmos does not mean disappearance. It means transformation. The Milky Way is littered with corpses, white dwarfs, neutron stars, black holes, the remnants of stars that exhausted their nuclear fuel and collapsed under their own gravity. billions of them scattered throughout the galaxy, invisible to casual observation but profoundly influential. White dwarfs are the most common. When a star like ours runs out of hydrogen, it swells into a red giant, sheds its outer layers, and leaves behind a dense core about the size of Earth. That core contains roughly the mass of an entire star compressed into a volume smaller than our planet. A teaspoon of white dwarf material would weigh several tons. The Milky Way contains an estimated 10 billion white dwarfs. They glow faintly with residual heat, slowly cooling over billions of years. Eventually, they will fade to black, becoming invisible cinders drifting through space. Neutron stars are stranger still. When massive stars explode as supernovas, their cores collapse beyond the white dwarf stage. Protons and electrons merge into neutrons. The result is a sphere only about 12 miles across, containing more mass than our star. A teaspoon of neutron star material would weigh about 6 billion tons. The Milky Way holds approximately 1 billion neutron stars. Some spin rapidly, emitting beams of radiation that sweep across space like lighthouse beacons. These pulsars flash with clockwork precision, some rotating hundreds of times per second. James Webb has observed regions where neutron stars influence their surroundings. The radiation and stellar winds from these objects shape nearby gas clouds. Shock waves from their formation trigger new generations of star birth. Death feeds life in an endless cycle. And then there are the black holes. Stellar mass black holes form when the most massive stars collapse. The Milky Way contains an estimated 100 million of them. Most drift silently through space, invisible except when they pass near other matter. A few betray their presence. When a black hole orbits close to a normal star, it can strip material from its companion. That material spirals inward, heats up, and emits X-rays detectable by space telescopes. These binary systems provide windows into black hole physics. Recently, astronomers discovered black holes through gravitational effects alone. The Gaia spacecraft detected stars wobbling as they orbited unseen companions. The masses of those companions exceeded what any normal object could provide. Black holes, confirmed through motion rather than light. The graveyard is vast. For every star you see in the night sky, there are dead stars you cannot see. They outnumber the living. They contain mass that influences galactic dynamics. They seed space with heavy elements from their explosive deaths. You pass through their legacy every day. The atoms in your body were forged in stars that no longer exist. Their remnants still orbit the galaxy, silent witnesses to transformations that happened billions of years before Earth formed. But the dead are not the only wanderers in the dark. Something else drifts between the stars. Worlds without homes, planets without parent stars, and there may be more of them than stars themselves. Imagine a world cast into eternal night. No sunrise, no seasons, no warmth from a nearby star, just a frozen sphere drifting through the void between stellar systems, alone in the darkness for billions of years. These worlds exist. Astronomers call them rogue planets, free-floating planets, nomad worlds, objects with planetary mass that orbit the galactic center directly rather than circling any particular star. Recent estimates suggest they might outnumber stars in the Milky Way. This is confirmed by multiple detection methods. Gravitational microlensing occurs when a massive object passes between Earth and a distant star. The object's gravity bends and magnifies the star's light briefly. By analyzing these events, astronomers can estimate the mass of the intervening object. Many microlensing events reveal masses consistent with planets, not stars, not brown dwarfs, planets. The statistics are staggering. Some studies suggest trillions of rogue planets wander the Milky Way. Others are more conservative, estimating merely billions. Either way, the number exceeds what anyone expected. Where did they come from? Most were probably ejected from their birth systems. When multiple planets form around a young star, gravitational interactions can become chaotic. Close encounters scatter objects onto new trajectories. Some fall inward toward their star. Others get flung outward into interstellar space. Simulations show this ejection process is common. Our own solar system may have lost planets during its early history. A hypothetical world, sometimes called Planet 9, might represent a survivor of this process, pushed to the outer reaches rather than ejected entirely. James Webb has detected rogue planets in nearby star-forming regions. The telescope's infrared sensitivity reveals objects too faint and too cool for previous instruments. In the Orion Nebula alone, Webb found dozens of free-floating objects with masses comparable to Jupiter. Some travel in pairs. Binary rogue planets, gravitationally bound to each other but not to any star, challenge formation theories. Did they form together and get ejected as a pair? Did they capture each other after separate ejections? The mechanics remain under investigation. Here is a thought that might unsettle you. A rogue planet could pass through our solar system and we might not notice until it was relatively close. These objects emit almost no light. They reflect nothing. They are dark wanderers, detectable only through their gravitational effects. Statistically, such encounters are rare. The distances between stars are vast, and rogue planets, though numerous, are spread across enormous volumes. But over the 4.5 billion-year history of our solar system, close passages have probably occurred. The galaxy is more crowded than it appears. Between the visible stars lie invisible worlds, cold, silent, drifting on trajectories that span millions of years. Some might harbor surprises. A large rogue planet with a thick atmosphere could retain internal heat from radioactive decay. Subsurface oceans might persist beneath frozen shells. Life, if it can exist without starlight, might find refuge in these wandering worlds. The darkness between stars is not empty, it is populated by exiles. And they carry secrets we have only begun to imagine. The Milky Way does not float alone in emptiness. It connects to something larger, a structure so vast that galaxies themselves become mere points along its strands. The cosmic web. Imagine the universe as a sponge. Galaxies cluster along the filaments of that sponge, connected by bridges of gas and dark matter. Between the filaments lie voids, regions nearly empty of matter that span hundreds of millions of light-years. Our galaxy sits within this architecture. The Milky Way belongs to the local group, a collection of over 80 galaxies gravitationally bound together. The local group in turn belongs to the Virgo supercluster, a larger structure containing thousands of galaxies. And the Virgo supercluster is merely one tendril of something even bigger, Laniakea. This supercluster complex spans over 500 million light-years. Its name means immense heaven in Hawaiian. Within its boundaries, approximately 100,000 galaxies drift toward a gravitational focal point called the Great Attractor. The Milky Way is falling toward the Great Attractor at roughly 1 million miles per hour. This motion combines with our orbit around the galactic center and Earth's orbit around our star. The velocities layer on top of each other, carrying us through space on a trajectory shaped by structures we can barely perceive. James Webb observes the cosmic web by studying distant galaxies. The distribution of those galaxies reveals the underlying filaments. Concentrations appear where filaments intersect. Voids appear where matter is sparse. The pattern repeats at every scale astronomers examine. Here is what makes this relevant to the Milky Way. Gas flows along the filaments. Fresh material streams into galaxies from the cosmic web, providing fuel for ongoing star formation. Without this inflow, galaxies would exhaust their gas supplies and stop making new stars within a few billion years. The Milky Way continues forming stars because it continues receiving deliveries. The gas arrives cold, often mixed with dark matter. It falls into the galactic halo, eventually cooling and settling into the disk, where it can collapse into new stellar systems. This is confirmed by observations of gas clouds falling toward our galaxy. High-velocity clouds, detected in radio wavelengths, represent material raining down from the halo. Their chemical compositions often differ from local gas, suggesting origins outside the Milky Way. We are not self-sufficient. The galaxy depends on its connections to the cosmic web. Sever those connections, and star formation would eventually cease. The Milky Way would age without renewal, its stellar population growing older until only fading remnants remained. The filaments are lifelines. They feed galaxies. They guide motions. They connect structures across distances that dwarf anything within a single galaxy, and they remind us that isolation is impossible. Everything in the universe links to everything else through gravity, through matter, through the web that underlies all visible structure. But the connections within our own galaxy hold surprises too. Stars that move so fast they are escaping entirely, fleeing the Milky Way at speeds that defy explanation. Some stars are running away, not drifting, not wandering, fleeing at velocities so extreme that the Milky Way's gravity cannot hold them. They will escape the galaxy entirely, destined to wander intergalactic space forever. Astronomers call them hypervelocity stars. The first was discovered in 2005. It moved at over 1.5 million miles per hour relative to the galactic center. Calculations showed it had been ejected from near the supermassive black hole roughly 100 million years ago. Since then, dozens more have been identified. The ejection mechanism involves extreme gravitational encounters. Picture a binary star system passing too close to Sagittarius A. The black hole's immense gravity can capture one star while flinging its companion outward at tremendous speed. The captured star spirals toward the black hole. The ejected star rockets away. This process is confirmed by computer simulations. The speeds depend on how close the binary approach the black hole. The closest encounters produce the fastest ejections. Some hypervelocity stars leave at over 2 million miles per hour. James Webb contributes to this research by characterizing hypervelocity candidates. Infrared observations reveal the temperatures and compositions of these stars. Spectra show their chemical signatures, helping astronomers trace their origins. Some hypervelocity stars appear to come from the galactic center. Others suggest different ejection mechanisms. Here is where the mystery deepens. Not all hypervelocity stars point back to Sagittarius A. Some trajectories suggest ejection from the galactic disk rather than the center. These stars might have been accelerated by different processes: supernova explosions in binary systems, close encounters with intermediate mass black holes lurking in star clusters, dynamical interactions in dense stellar environments. The Gaia spacecraft has revolutionized this field by measuring the precise positions and motions of nearly 2 billion stars. Gaia identified candidates moving fast enough to eventually escape. Some are already beyond the main disk, climbing out of the galactic gravitational well. They carry information with them. The chemical composition of a hypervelocity star records where it formed. If it originated near the galactic center, its elements reflect the enriched environment there. If it came from the disk, different patterns appear. These stars are messengers. They sample regions of the galaxy difficult to study directly. They reveal conditions that existed when they were ejected, sometimes hundreds of millions of years ago. They test our understanding of extreme gravitational dynamics, and they raise an unsettling question. How many stars has the Milky Way lost over its history? If the ejection process has operated for billions of years, countless stars have escaped. They now drift through the voids between galaxies, forever separated from any stellar system. Dark wanderers that once belonged to our home. The galaxy leaks. It gains mass from infalling gas and consumed satellite galaxies. It loses mass through hypervelocity ejections and evaporating halos. The balance determines our galaxy's fate. But fate operates on timescales almost too long to comprehend. And the timeline for our own stellar neighborhood holds its own transformations. An invisible force threads through the entire galaxy. It bends, it twists, it shapes the motions of charged particles across distances spanning tens of thousands of light years. The galactic magnetic field. You cannot see it, you cannot feel it, but it influences everything from cosmic ray propagation to star formation to the structure of gas clouds throughout the Milky Way. The field strength seems weak by everyday standards, roughly 100,000 times weaker than Earth's magnetic field. A refrigerator magnet overpowers it by an enormous margin. Yet, across galactic scales, this faint magnetism accumulates into something significant. Charged particles spiral around magnetic field lines, cosmic rays, the high-energy protons, and atomic nuclei that zip through space follow twisted paths dictated by the field. Without this guidance, they would travel in straight lines and escape the galaxy quickly. The magnetic field traps them, bouncing them back and forth for millions of years. This matters for life on Earth. Cosmic rays that reach our planet contribute to background radiation. They trigger mutations. They may have influenced the evolution of life over billions of years. The magnetic field that contains them shapes how many arrive at any given location. James Webb does not directly observe magnetic fields, but it sees their effects. Polarized light from dust grains reveals the field's orientation. The tiny particles align with magnetic field lines, preferentially blocking light vibrating in certain directions. By measuring this polarization, astronomers map the invisible architecture. Recent studies revealed the field's structure in unprecedented detail. Near the galactic center, the field becomes chaotic. Twisted filaments of magnetized gas point in seemingly random directions. The needle-like structures Webb observed in Sagittarius C may trace these tangled magnetic loops. Farther out, the field follows the spiral arms. Gas and dust moving through the arms drag the field with them. The magnetic lines stretch and compress, amplified by the differential rotation of the disk. The field becomes woven into the galactic structure itself. Here is something that might surprise you. The origin of the galactic magnetic field remains uncertain. Astronomers know magnetic fields can be amplified through a process called the dynamo effect. Conducting fluids in motion generate and strengthen magnetic fields. The rotating, turbulent disk of the Milky Way provides ideal conditions. But this process requires a seed field to amplify. Where did that original magnetism come from? Some theories suggest primordial fields generated in the early universe. Others propose that the first stars created magnetic fields through their deaths. The answer remains a mystery under active investigation. What is certain is that the field exists and matters. It influences how gas clouds collapse into stars. It channels energy from supernovas and stellar winds. It connects distant regions of the galaxy through invisible magnetic bridges. You live inside a magnetized structure. Every atom of your body exists within the galactic field, embedded in a web of force that spans 100,000 light years. And that field carries traces of events that happened before our planet existed. Some stars break the rules. They contain so little of the heavy elements forged in previous stellar generations that they seem to predate the processes that created those elements. They should be impossible. Yet they exist. Astronomers call them ultra-metal-poor stars. Their atmospheres contain less than 1/10,000th the heavy element content of our star. Some contain less than 1/1,000,000th. These objects formed from nearly pristine gas. Gas that had been barely touched by the ashes of previous stellar deaths. Gas that closely resembled the primordial material produced in the Big Bang itself. Finding such stars in the Milky Way tells us about the galaxy's earliest history. The first generation of stars formed from pure hydrogen and helium. They contained no carbon, no oxygen, no iron. When they exploded, they seeded the universe with the first heavy elements. We have never directly observed a first-generation star. Theory suggests they were massive and short-lived. They would have burned through their fuel and exploded within a few million years of forming. None should survive today, over 13 billion years later. But their immediate descendants might second-generation stars formed from gas slightly enriched by first-generation explosions. These objects would contain trace amounts of heavy elements, enough to alter their structure, enough to allow some of them to survive for the entire age of the universe. James Webb searches for these survivors in the galactic halo. The halo contains the oldest stellar populations, stars that formed when the Milky Way was still assembling, before the disk had settled, before the spiral arms had developed. Recent observations identified stars with astonishing chemical signatures. One object contained heavy elements at levels consistent with enrichment by a single supernova. That star might have formed from a cloud seeded by just one first-generation explosion, a direct link to the universe's earliest epoch. Here is what makes these discoveries profound. These ancient stars are time capsules. Their compositions record the chemistry of the gas from which they formed. By studying them, astronomers can reconstruct conditions that existed billions of years before Earth. Some ultra-metal-poor stars show unexpected patterns. Elements appear in ratios that do not match standard supernova models. The first stellar explosions might have operated differently than modern ones. The physics of stellar death might have changed as the universe evolved. Each ancient star carries clues. The mystery of the first stars, objects we may never observe directly, becomes tractable through their descendants. The Milky Way preserves this history in its oldest members. You share a galaxy with objects that formed when the universe was a fraction of its current age. They have orbited the galactic center perhaps 50 times since their birth. They have witnessed the assembly of the disk, the growth of the spiral arms, the consumption of countless satellite galaxies, and they are still burning. Faint, ancient, impossible by simple expectations, but real. Space is silent. Sound requires a medium to travel through. Vibrating air molecules carry waves to your ears. In the vacuum between stars, no molecules exist. No vibrations propagate. No sound reaches across the void. But if you could hear it, the galaxy would roar. Every process that shapes the Milky Way involves motion and energy. Colliding gas clouds, exploding stars, collapsing cores, orbiting binaries, infalling material. If these events occurred in an atmosphere instead of vacuum, they would produce sounds beyond imagination. Scientists have translated some cosmic phenomena into audio. By converting electromagnetic signals into sound waves, they create audible representations of what telescopes detect. The results are haunting. The supermassive black hole at the galactic center produces pressure waves in surrounding gas. These waves ripple outward like sound waves in air, though at frequencies far below human hearing. By shifting the pitch upward by many octaves, researchers created an audio file of the black hole's vibrations. It sounds like a deep, rumbling groan, a cosmic moan echoing through the galactic center. Pulsars produce rhythmic signals. The spinning neutron stars emit beams of radiation that sweep past Earth at regular intervals. Converted to audio, they click and pulse like alien heartbeats. Some spin so fast their signals blend into continuous tones. Solar-type stars oscillate. Pressure waves bounce through stellar interiors, causing the surface to vibrate. These stellar quakes can be detected through brightness variations. Converted to sound, stars hum and ring like enormous bells. James Webb detects infrared light, not sound. But the phenomena it observes would generate incredible acoustics if media existed to carry the waves. Star-forming regions would crackle with the sounds of collapsing clouds. The shock waves from newborn stars blowing bubbles in surrounding gas would boom like thunder. The jets from protostars would hiss and roar as material blasts outward at hundreds of miles per second. Supernovas would deafen anything nearby. The shock waves from exploding stars sweep through interstellar gas at thousands of miles per second. If that expansion occurred in air, the sound would exceed anything on Earth by countless orders of magnitude. The galaxy is a symphony of violence. Constant creation and destruction, endless motion, energy transferring from form to form across billions of years. We experience it in silence only because vacuum separates us from the action. Gravitational waves offer another form of cosmic sound. These ripples in space-time carry information about the most violent events in the universe. Black holes merging, neutron stars colliding. When detectors register these waves, scientists convert them to audio. The chirps and rings of gravitational wave signals represent the universe speaking in a language we have only recently learned to hear. The Milky Way hums with gravitational radiation too. Background waves from countless sources blend into a cosmic murmur. Future detectors will tune into this signal, listening to the galaxy's gravitational voice. Silence is an illusion of distance. The universe screams. We simply lack the ears to hear it directly. But we are learning to translate. Our solar system floats within a void, not the emptiness of intergalactic space. Something smaller, something local, a cavity carved into the gas and dust of the galactic disk, the local bubble. This structure spans roughly 1,000 light-years in diameter. Within it, the density of interstellar gas drops to a fraction of the surrounding average. We exist in a pocket of relative emptiness. Something cleared this region. Supernovas. Approximately 14 million years ago, a series of massive stars exploded in our cosmic neighborhood. The blast waves swept outward, pushing gas and dust ahead of them. The expanding shells created a cavity that persists today. This is confirmed by multiple lines of evidence. Radioactive isotopes found in ocean sediments match the timing of nearby supernovas. The distribution of young stars in our vicinity traces the edges of the bubble. X-ray observations reveal the hot, thin gas that fills the cavity. James Webb studies star-forming regions at the bubble's boundaries. Where the expanding shell meets denser interstellar material, compression triggers new stellar birth. The supernovas that created our empty neighborhood are indirectly responsible for stars now forming around its edges. Here is something remarkable about our position. We sit near the bubble's center. The explosions that carved this cavity happened relatively close to where our solar system currently orbits. We may have passed through the blast zones. Earth may have experienced elevated radiation during those events. Some researchers speculate about biological effects. Increased cosmic ray flux could have influenced mutation rates. Climate changes might have occurred as Earth's atmosphere interacted with supernova debris. Mass extinctions in the fossil record roughly coincide with estimated explosion dates. These connections remain theories requiring further study. What is certain is that our galactic environment has changed dramatically over millions of years. The local bubble will not last forever. Eventually, the hot gas will cool. The cavity will fill with material from surrounding regions. Future generations, millions of years from now, will occupy a different interstellar environment than we experience today. Our neighborhood is temporary. The stars we see at night, the constellations that seem eternal, represent a snapshot of a dynamic system. The nearest stars move relative to us. Over tens of thousands of years, familiar patterns will distort and dissolve. New patterns will form. Different stars will become our neighbors. Different supernovas will reshape the local medium. The bubble we live in will be replaced by other structures, other cavities, other consequences of stellar death. We are always passing through. The galaxy does not hold still for anyone. It reconfigures constantly, on timescales just long enough that human lives cannot perceive the changes. But the changes accumulate, and they point towards something that awaits everything in the universe, an ending that physics describes with unsettling certainty. Nothing lasts forever. Every star in the Milky Way will eventually die. Every light that illuminates the galaxy will fade. Given enough time, the brilliant spiral we call home will go dark. This is confirmed physics. Stars shine by converting hydrogen into helium through nuclear fusion. This process releases energy that counteracts gravity, supporting the star against collapse. But hydrogen supplies are finite. Small stars burn slowly. Red dwarfs, the most common stars in the galaxy, can continue fusing hydrogen for trillions of years. Some currently burning red dwarfs will still be shining long after every other type of star has died, but even they will exhaust their fuel eventually. When fusion stops, gravitational collapse resumes. The stellar core compresses into a white dwarf, neutron star, or black hole depending on its mass. The object cools over billions of years, fading from visibility. The Milky Way is already aging. Star formation rates have declined compared to the galaxy's youth. The raw materials for new stars, gas and dust, are being consumed faster than they are replenished. Eventually, the supply will run out. When star formation ceases, the countdown begins. The most massive stars will die first, within millions of years. Medium-mass stars like ours will follow, over billions of years. Finally, the red dwarfs will begin to expire, a process stretching across timescales that dwarf the current age of the universe. James Webb observes galaxies at various stages of this evolution. Some galaxies have already stopped forming stars. They appear red because only old, cool stars remain. These quiescent galaxies reveal what the Milky Way might become in the distant future. Here is the timeline that physics predicts. In about 5 billion years, our star will exhaust its hydrogen core. It will swell into a red giant, shed its outer layers, and leave behind a white dwarf. By then, the Milky Way and Andromeda will have merged or begun merging. The combined galaxy will contain aging stellar populations. Star formation will continue in diminishing bursts until the gas is gone. Over the following trillions of years, stars will die one by one. The galaxy will dim. White dwarfs will cool toward absolute zero. Neutron stars will spin down and fade. Black holes will persist longest, slowly evaporating through a process called Hawking radiation. Eventually, nothing will remain. No stars, no warmth, no light, just cold remnants drifting through expanding darkness. This fate awaits not just the Milky Way, but every galaxy in the universe. The cosmos will not end with a bang. It will end with a whisper, a slow fade into eternal night.